Hey everyone, Dave here with another dose of Commodore history for you. If you've been watching the channel for a while, you might remember a while ago I did an episode about why the Commodore 64 and the 1541 disk drive were so slow at loading programs. And I was never really happy with how that episode turned out for a couple reasons. One was it was very incomplete. I talked about why the VIC-20 and C64 were so slow, but I never talked about what Commodore did to fix that. And they did fix it when they released the C128 and the 1571. The other reason I didn't like that video is because the benchmark tests that I did in that video were absolutely repugnant. And it's my own fault. I knew they were bad before I even published it, but I was too lazy to go back and fix them. So I have to live with that. The video started getting a bunch of views and I didn't want to take it down and put it back up. So it's out there for better or for worse. Now this video, I intended to go back and do a follow-up and just fix part one of that. Hey, yeah, the VIC-20 and C64 were slow, but here's how they fixed it with the C128. But I figured, well, at the beginning, I'll do a short recap. I'll just cover the VIC-20 and C64, it'll be quick, and then I'll move on to the C128. But when I started doing that quick recap, I realized there's a third thing about the previous episode that I didn't like. I did a really awful job of explaining some of the concepts, so I thought, well, I'll do a better job this time. Now, what does that mean? Well, if you already saw the previous video, a lot of this one's going to seem redundant, and I'm sorry about that. If you haven't seen it, though, I really hope you'll appreciate the time and effort I put into it to make this one a lot easier to follow and to make it make more sense. So, you're probably done hearing me talk. Let's get started. Quick recap of why the C64 and 1541 were so slow. Commodore's first computer, the PET, and their first disk drive, the 2040, used parallel data transfer, so all 8 bits of every byte were sent across the bus in parallel. When Commodore released the VIC-20 and its first disk drive, the 1540, mainly for cost reasons, they switched to doing serial data transfer. So instead of 8 bits being sent at the same time, each bit was sent across the bus in single file. This shouldn't have been that bad. After all, Commodore owned MOS technology. When they bought the chipmaker in 1976, they got Chuck Peddle, the 6502 CPU, which allowed them to enter the computer market with the PET, and they got a stable of custom silicon, including the 6522 VIA chip. The VIA was a souped-up clone of Motorola's 6820 PIA, or Peripheral Interface Adapter, with a few bonus features, one being a serial shift register that Commodore planned to use for the VIC-20's disk I/O. By using a 6522 VIA in the VIC-20 and in the 1540 disk drive, serial data transfer would be achieved by simply writing a byte to the 6522's shift register on the sending side. The 6522 would internally shift off each bit and send it across the serial data pin along with a clock signal. The receiving side 6522 VIA would shift the incoming bits in, and the receiver would read the byte from the shift register. All the bit shifting and transmitting would happen in silicon, so it would be super fast. I'll take a few minutes to demonstrate this for you because I think it'll help you to understand just how simple this would have been if you can watch it work. The two chips in the upper left corner here are the 6522 VIA chips. According to the 6522 datasheet, the serial clock and data lines, CB1 and CB2, are pins 18 and 19. I'll connect logic analyzer probes to these pins so we can watch how easy it is to send serial data using the 6522's shift register. I'll need to type on the VIC-20, so instead of removing the keyboard to attach these probes, I just moved it to the side to make room. Alright, probes are connected to CB1 and CB2, now I just need to connect a ground probe. I'm going to do a quick demonstration of how to use the 6522 shift register so you can see how it works. But before I do, I want to make it very clear, this isn't a real world example. There's a lot of setup you need to do before you use the shift register, and I'm skipping all of that in my demonstration. I'm doing the bare minimum I possibly need to do so that I can make signals go across the wire. So let's get started. For my example, on the right is the VIC-20's monitor, and on the left you see the output of the logic analyzer. The white line on top represents the digital signals on the CB1 clock line. The brown one underneath that is the CB2 data line. Right now they're both high or near 5 volts. This first poke command, the details are on the screen if you care, but you don't need to worry about it. It's telling the 6522 which mode I want the shift register to operate in. And this poke tells the 6522 the value of the byte I want it to shift out. I randomly picked decimal 65. And magic! The moment I pressed enter, you saw the signals go across the data and clock lines. I'll zoom in on them. That way we'll be able to see what they look like. I'm zoomed in. You can see channel 0 is CB1, channel 1 is CB2. H indicates where the signal is high or near 5 volts. L indicates where the signal is low or near 0 volts. The signal on the data line is valid with the rising edge of the clock signal. So over here on the right, where the clock is rising, the data line is high, so that's a 1 bit. The 6522 sends data most significant bit first, so this is the least significant bit, or bit 0. That's followed by 5 0 bits, then another 1 bit. Finally, bit 7 is a 0. As expected, binary 01000001 is decimal 65, which is the byte we told the shift register to send. Notice over here I've got a 9th clock pulse. I'm not 100% sure why, and I'm not going to dig in to find out in this video because it's not important. As I said earlier, I skipped all the necessary setup stuff, so it could be related to that, or it could be one of the 6522 bugs listed in the Synertech datasheet for the 6522 VIA. Synertech was a second source supplier for the MOS 6522, and while the MOS Technology 6522 datasheet doesn't mention any bugs, the Synertech one devotes an entire page to documenting bugs and irregularities in the 6522. This highlighted issue here documents a 9th clock pulse, so maybe that's what happened in my demonstration. Regardless, I needed to mention the 6522 bugs anyway, because bugs in the 6522 shift register are why the VIC-20 ended up not using the 6522 shift register for serial disk I/O. The initial VIC-20 hardware design and kernel serial routines used the shift register, but Bob Russell said the bus kept locking up during testing, and they eventually determined it was caused by a bug in the 6522 shift register. They discovered this very late in the development cycle of the VIC-20, so late in fact that this telex from Michael Tomczak to Tony Tokai at Commodore Japan Limited suggests the first VIC computers may not have serial capabilities. Is this a potential problem, Michael asked? You bet it was. So Commodore found themselves in a little bit of a pickle. They had a VIC-20 computer almost ready to ship, and it didn't have a working serial bus. So what did they do? Well, they couldn't use the MOS 6522's shift register functionality, but they could certainly use the other pins on the 6522, like the peripheral I/O pins, and that's exactly what they did. So let's talk about the details. Let's take a look at this schematic diagram for the VIC-1001 computer. When the VIC-20 was initially released in Japan, it was called VIC-1001, so this is effectively a very early VIC-20 schematic. If I make everything disappear except the serial bus, it looks a lot less daunting. We can make it even simpler by removing the control lines, attention and reset, leaving just the clock and data lines, because for now, I just want to explain what they did instead of using the 6522 shift register. Now, all that provided was a clock and data line, so I'll show how Commodore implemented the clock and data serial lines without using the shift register. The schematic shows they use PA0 and PA1 as clock and data inputs. The PA and PB pins are peripheral application pins, or what you'd call general purpose I/O pins today. They can be programmatically set to act as inputs or outputs. In this case, they're being used as inputs. So these two pins are reading clock and data signals sent from the disk drive. They used CA2 and CB2 as output pins to drive the clock and data lines. These are actually control pins and provided significant additional functionality to the 6522 compared to the general purpose peripheral I/O pins, but in this case, they're configured in what's called manual output mode, where they can be set high or low in the same manner as the peripheral I/O pins. So these 4 pins on the 6522 are all perfectly capable of sending and receiving serial data in the same manner as I already showed the shift register did. But the key difference is that the serial implementation must be done in software. So instead of the CPU writing an 8-bit byte to the shift register and the 6522 shifting off the bits and sending them across the wire, the CPU would have to do the work to do the bit shifting
and the CPU will have to manipulate CA2 and CB2 high and low to send the serial data signals across the bus. This animation should help to illustrate what I'm describing. If we start out with a byte on the VIC-20 that we want to send to the 1540 over the serial bus, it's all software driven. Code running on the VIC-20 has to shift the first bit off, then it has to manipulate the CA2 and CB2 lines of the 6522 to create the clock and data signals on those lines to send the bit to the 1540. The DOS code in the 1540 uses a 6522 to read the input lines and reassemble the byte on the other end one bit at a time. And this process is repeated for each bit until all 8 bits have been sent. Now, some suspension of disbelief is required for this animation. The way the 6502 tells the 6522 which output pins to enable is by writing a byte to a 6522 register with a bit mask that corresponds to the peripheral pins you want to activate. I'm not showing that whole byte being written here, but that's okay. The important thing to recognize is that instead of the 6502 doing a single write to the shift register to transmit a byte, it's manually shifting each bit off and manually manipulating pins on the 6522 to create the serial bus signals for each bit. Alright, before I move on, let's take a quick moment to talk about the history behind this. Who wrote the serial routines for the VIC-20 kernel? Well, I find myself on Zimmers.net, the holiest of holies for anything related to Commodore, and look what we have here. Assembly source for VIC-20 kernel and basic ROMs. That is minty fresh goodness right there. I downloaded that and untarred it. What you're looking at here is the tail end of the serial implementation. And these comments tell us who wrote the serial implementation. Bob Fairbairn, username RJF, wrote the initial code between August 11th and August 26th, 1980. Username RSR is Bob Russell. He cleaned up the serial code and fixed some bugs between September 8th, 1980 and October 7th, 1980. Let's talk about those dates. The VIC-1001 was publicly unveiled the weekend of September 19th, 1980, and Commodore began taking pre-orders there. Bob Russell didn't finish the serial code until October 7, 1980. So let's stroll over to the VIC registry at cbmvic.net to get some date codes. The earliest VIC-1001 on the list, serial 100282, has the latest chip date code of 4480, which means that chip was made in the 44th week of 1980, which was the week of October 27, 1980. So Bob Russell finished working on the serial code October 7, and they were already completing mask ROMs on October 27th. Imagine the stress levels at Commodore trying to get the VIC-20 out the door. Great history there. Let's get back to business. Much like I showed you what the 6522 shift register serial clock and data signals look like with the logic analyzer, now I'll show you what Commodore's software implementation looks like. I'm connecting the logic analyzer to pins 2 and 3 here, which are PA0 and PA1. Now, these are the serial clock and data input pins, the pins that read data sent from the drive. But that's okay, because if you look over here, you'll notice they're connected to the output pins anyway, so we'll see the output signals on these pins. I'm doing this because they're on the output side of the 7406 inverters, so the logic levels will make more sense. Now, for this demonstration, I need to have a disk drive connected. I didn't for the earlier one. The kernel's serial code won't send data if a drive doesn't respond to it. Now, there's not even a disk in the drive, but it doesn't matter. The VIC-20 will send data bytes across the bus asking for the drive to load a file, and we can inspect those data bytes. Here's a byte of data being sent across the serial bus from the VIC-20 to the 1541 disk drive. It looks a lot like what the 6522 shift register did, but there are some differences. First, let's talk about how handshaking works, or how the sender knows the receiver is ready to receive data. With Commodore's serial bus, the roles of sender and receiver can flip. When the VIC-20 sends commands to the 1541 drive, it's the sender and the 1541 is the receiver. When the 1541 reads data from disk and sends it across the bus to the VIC-20, the 1541 is the sender and the VIC-20 is the receiver. The protocol is exactly the same in either direction. Here, the sender, which is the VIC-20, is holding the clock line low. This tells the receiver, the 1541, it's not ready to send a byte. Likewise, the 1541, as the receiver, is holding the data line low, indicating that it's not ready to receive a byte. When the sender's ready to send a byte, it releases the clock line high. When the receiver is ready to receive a byte, it releases the data line high. Once this happens, the sender takes control of both the clock and data lines. The sender pulls the clock line low now and the handshake is complete. The rest of the sequence is a byte of data being sent. Unlike the 6522 shift register, which sent data with the most significant bit first, Commodore's software serial implementation sends data with the least significant bit first. Data is valid with the rising edge of the clock. So here where the clock signal is rising, this signals that the first bit of data is valid. The data line is low, so the first bit is a 0. Then we have a 0, 0, 1, 0, 1, 0, 0. 001, 01, 000 is hex 28. So the VIC-20 sent a bus control code hex 28 to the 1541 disk drive. With the entire byte sent, the VIC-20 pulls clock low and releases data high, relinquishing control of the data line. The 1541 then pulls data low, and we're back to the initial state, waiting for the next byte to be sent. Let's take a live look at the logic analyzer now. I have 2 sessions open in it. This one is a byte being transmitted using Commodore's slower software-based serial implementation. Now, this is what the VIC-20 actually used. If I look at the other tab, this is a byte being transmitted using the 6522 shift register, which Commodore couldn't use. Remember earlier I mentioned there were some bugs in the shift register implementation. So they look about the same, right? Well, if I take some measurements, you'll quickly understand just how different they are. Now I'm back here on the slow serial implementation, and I'll measure starting where the clock is released high, right to the end where the clock is pulled low. And we get 905 microseconds delta t. If I go back over here to the shift register implementation, we'll measure this from beginning clock to ending clock, and we get 16 microseconds. And that's a pretty big difference. The slow serial bus can transmit a byte of data in 905.4 microseconds, which works out to 1104.5 bytes per second. This does not take protocol overhead into account, like waiting in between bytes, selecting and unselecting devices on the bus, sending DOS commands and receiving responses. It also doesn't take drive seek time into account. Actual benchmark times doing real data transfer are less than half that, at around 400 bytes per second. The shift register spit out a byte in 16.64 microseconds, which works out to 60,096 bytes per second. All the same caveats apply. This is not representative of what actual data transfer rates would be. And also, remember there's an extra clock pulse in that measurement that doesn't belong. Well, this does illustrate the Commodore serial bus protocol would not have been nearly as slow if they could have used the 6522 shift register like they intended. Bob Russell was the primary engineer on the Commodore VIC-20, and I just described how he was burned by the buggy 6522 shift register on that project. But he got a second chance when he was working on the Commodore 64 project. A new 6526 CIA chip was available with a working shift register, and the plan was to use a 6526 in the C64 and the 1541 disk drive. Finally, fast serial disk I/O. Unfortunately, through a series of comical misadventures like production engineers removing the necessary fast serial traces from the PCB, the C64 ended up using the same software-based serial disk I/O routines as the VIC-20, and due to VIC-2 timing issues, C64 disk I/O is slightly slower than the VIC-20. I talked about that in more detail in my previous video on this topic, so check that out if you're interested. Commodore tried and failed to implement fast serial disk I/O on the VIC-20 in 1980. They tried and failed again with the Commodore 64 in 1982. In 1985, with the Commodore 128 and 1571 disk drive, they were not denied. The Commodore 128 and 1571 both contained MOS 6526 CIA chips with a working shift register, and Commodore delivered a fast serial bus to the masses. Commodore 128 here, 1571 disk drive here. Now, if we want to be able to watch signals on the wire, Logic analyzer here. So to be able to hook that up, we're going to need to take the top case half off the 1571. I already had the screws out of there to make it simpler. Now, the difficult thing that we have to deal with here is the PCB is underneath the power supply on the 1571. And there's not a lot of room here to move. Like, you can't really lift this up and move it out of the way. So what I had to do was, this is the power here. I disconnected the power, and then I made an extension for it. I used Molex connections and everything, and I almost even got the wires the right color, but I didn't have brown, so I used yellow. I even used zip ties, so it's basically factory. Now, what I didn't do is use the right size connector. If you take a look at this, it doesn't actually plug in there. It almost fits, but not quite. But what I learned is, if I just jam it into here, I can make it work. So that will allow me to move the power supply back here, jam this in there, and then plug that into the board. It's not going to be pretty, but it'll do what we need. Once the power supply is out of the way there, I'll get the logic analyzer hooked up here, and we'll be able to watch some signals go across the wire when we load programs. Now we're ready to talk about Commodore's fast serial mode. What you're looking at is every signal that crossed the bus from the moment I powered on the C128 through me loading a program from the 1571. At a high level, these signals here are the C128 and the 1571 going through their boot sequence and initializing various registers. And it's the C128 sending the I, or initialized DOS command to the 1571. This is the C128 reading the boot sector to see if it can auto boot. And then over here is where I issued the deload command on the C128, and the 1571 loaded data from disk and sent it over the bus to the C128. I can't cover every detail in this video for reasons of time, and honestly, there are still details in the protocol that I don't fully understand. But I'll cover all the high points, and when we're done here, you'll know a lot more about Commodore's fast serial protocol. I'll zoom in right here to get started. What you're looking at is the older, slow serial protocol. Commodore's fast serial bus protocol didn't replace the original slower protocol. Rather, fast serial was built on top of the original serial protocol. Anywhere the attention line is pulled low, which it is here, that means bus control codes are being sent. And even on the C128, when talking to a 1571, bus control codes are sent using slow serial protocol. Over here on the left, however, is the first sign that something is different with the C128 and 1571. The first thing you'll notice is there's a signal on the service request line. The service request line wasn't used on the VIC-20 and C64. If you look at Commodore serial cables, they were the same for every computer that supports Commodore serial protocol, from the VIC-20 through the C128. Pin 1, service request, pin 2 is ground, pin 3 is attention, pin 4 is clock, pin 5 is data, and pin 6 is reset. So the service request line was always there in the cable, but it wasn't used until the C128. So what is this signal on the service request line? It's how the C128 tells a connected peripheral that it wants to do fast serial. It's called a host request fast, or HRF signal, and it's nothing more than the data byte hex FF. It's simple, but pretty clever. Doing this on the SRQ line allowed Commodore to maintain compatibility between all their serial-capable devices. The 1571 boots into a natively 1541 compatible mode by default. When the C128 sends this HRF signal across the SRQ line, the 1571 detects that and can transition to 1571 mode, which supports fast serial. If the C128 is connected to a 1541 drive, the drive won't see this signal, so it won't respond to it. This way, the C128 knows not to talk fast serial to the 1541. Likewise, if you connect a C64 to a 1571 disk drive, the C64 won't send an HRF signal over the SRQ line because the C64 doesn't have any concept of fast serial mode, so the 1571 remains in 1541 compatibility mode when connected to a C64. Pretty clever. The last thing I want to mention is that the HRF signal isn't just sent once when the C128 boots. It's sent at the beginning of every command loop, so fast serial is constantly negotiated between the computer and the disk drive throughout their conversation. Over here, this hex 0 byte is the 1571 sending a device request fast, or DRF, signal back. It's the 1571 responding to the C128's HRF signal, letting the C128 know that it's eager to use fast serial protocol. So at this point, the 1571 knows the C128 can talk fast serial protocol, and the C128 knows the 1571 can talk fast serial protocol. There's some random chatter on the bus where the C-128 sends an I or initialized DOS command to the 1571, then it sends a command asking the drive to read track 1 sector 0. Incidentally, this is why you always see disk drive activity when you boot a C-128. It's looking for an auto boot sector. So I'll scroll over here to where things get interesting. This is the 1571 returning the 256 bytes of track 1 sector 0 to the C128, and it's doing so using fast serial protocol. I already pointed out the obvious, that the SRQ line is being used for fast serial, so how does that make serial I/O any faster? Well, because it's being driven by the serial shift register in the 6526 CIA chip instead of CPU bit banging. If you look at how fast serial was implemented, it's pretty neat. I'll start with how handshaking works. Handshaking works just like it does with slow serial, which I described earlier in the video. The 1571, which is the sender, is holding the clock line low. It's not ready to send data yet. The C128, which is the receiver, is holding the data line low. It's not ready to receive data. Once the 1571 is ready to transmit a byte, it releases the clock line high, then the C128 responds by releasing the data line high to indicate it's ready to receive a byte. The 8-bit byte is transmitted by the 6526 shift register using the SRQ line as the bit clock and the data line to transmit the data bits. In this case, the byte is a 0. There isn't a boot sector on this disk, so every byte in track 1 sector 0 is a 0. I'll zoom way back out now. Then move over here to where I executed a deload command on the C128 so we can see what happens on the wire. Attention is pulled low, so this is the C128 sending a bus control code to the 1571 using slow serial, and it's a hex 28, which is the bus control code for listen device 8. Moving right along here, another bus control code, and this one is hex 6F, which means open channel F, or 15 in decimal. 15 is the command channel, so the C128 will be sending a CBM DOS command to the 1571 next. And the first byte of that DOS command is hex 55, or PETSCI character U. And next we have PETSCI 0. Before I move on, let's take a look in the 1571 user manual to see what the U0 command is. Chapter 10, Burst Commands. This section of the manual describes Commodore's Burst Command Instruction Set, or BCIS. The first command shown in the manual is the read burst command. Byte 0 of the read command is 01010101, which is hex 55, which is PETSCI U. Byte 1 is 00110000, which is hex 30, which is PETSCI character 0. I'll save us some time and tell you that every burst command starts with U0. These were also called the user 0 commands. So the next byte, that's going to tell us which burst command is being issued. And that byte is 0001111, which is hex 1F. Page 87, the fast load burst command. Again, byte 0 and 1 are U0. Byte 2 is 0001111, or hex 1F. So the C128 sent a fast load burst command to the 1571. Byte 3 is the file name, so we should see that next. First byte of the file name is hex 30, which is PETSCI 0. Hex 3A, PETSCI colon character. I don't know why this one was sent as a slow byte, but anyway, it's a Petsky asterisk character. Recall the deload command I typed was deload quote asterisk quote. The drive number of 0 is implied there, so the kernel parsed R asterisk and then sent 0 colon asterisk to the 1571 as part of the BCIS fast load command. I'll zoom way out here, then scroll over to where the 1571 starts sending data back to us so we can see if there's something different about the fast load burst command compared to the fast serial data transfer we examined earlier. Yeah, this is different. The earlier fast serial protocol we examined was slow serial handshaking with the actual data bit being clocked out by the 6526 shift register. So the data transfer was faster, but the handshaking was still slow. What you're looking at here is how the BCIS fast load protocol works. The sender, which is the 1571 in this case, controls the service request and data lines. The receiver, which is the C128, controls the clock line. The only handshaking that takes place is that the receiver toggles the clock line every time it's ready to read another byte. Over to the left here, the C128 pulls clock low. It's ready to read a byte. The 1571 sends a byte using service request and data, then waits for the 128 to toggle the clock line. The C128 releases clock high, and the 1571 sends another byte. Lather, rinse, repeat.
Alright, here we are. I think I did a pretty good job this time of explaining slow serial, how it came about, why it was slow. I also am pretty happy with explaining fast serial. I didn't cover every single detail, but I think we have a pretty good understanding of what it means and how it works. One thing that I didn't talk about though was, before I started this video, I was confused about terminology. I've really heard burst mode and fast serial used interchangeably. I don't think that's accurate. I think what we saw here, or at least how I interpret it, is fast serial is the first bit I showed you where it's using the shift register to transmit the bits, but it's using the old slow serial handshaking. I think that's fast serial. And burst mode, I would call that the burst command instruction set fast load command when it does the super fast clock-based handshaking. So anyway, that was a new one for me. I don't know what you think about that. Maybe you disagree, maybe you agree, let me know. I was going to just close here, but I thought, well, I'll do a tiny bit of benchmarking. Now, we know from previous episodes how great I am at doing benchmarking. And by great, I mean really, really awful. But I'm going to keep it very simple here and hopefully not do anything too stupid. So let's take a look at that.
I'm sending a command to the 1571 to force it into slow serial mode. Now I'll load a 15K program file I created earlier and save to the disk. And notice in the logic analyzer output there are no SRQ signals. It's doing slow serial disk I/O here, which is what we wanted. Okay, reset and do a simple deload of the same file, which will use the burst fast load command. Okay, now we measure. First, burst mode. That clocked in at 4.95 seconds, which would put the average transfer rate at 3,102 bytes per second. Slow serial clocked in at 40.48 seconds, so an average transfer rate of 379 bytes per second.